Good morning, you guys. Here you have a little bit of a digital me to start off your day. You guys will, if you ever have the pleasure of becoming a teacher, it is the best job ever. The only downside to it is when you're gone, and actually being gone is way more work because you have to kind of stuff an additional work day outside of the day because you plan the whole day and then you have to implement it for somebody else to do, which is great because we have these wonderful people that do that for us. But it's like a double time. You kind of have to work double to get it to go. And so I never like being gone. It's never any fun. So this part, however, I'm going to act like I'm there. I'm going to record these. I always liked making these videos, and that kind of helps keep things rolling when I'm not there. But there's a vertical asymptote. X equals 0 was the way we left off. Do you remember that yesterday? We were talking about discontinuity types, and that's one of them. And then we talked about a jump here. So I'm just letting you to kind of get your ducks in a row while this video gets rolling, just reviewing where we left off yesterday, because we're going to continue from here. Remember, there's the hole up here, and then there's this misplaced point. That was the other kind. And one of these, if I can do this, misplaced point, when you guys do your homework for my math lab, these are non-removable, and the one that is removable is the hole, and that, for my purposes, isn't important, but it's if you guys want to finish up the homework and know what that means, this is the removable kind. I just refer to them by their name, so nothing you need to get too caught up in. The last picture on here, so those were types of discontinuity, places where you'd have to lift your pen and the names that go with them. The last one, continuous. Those are functions that don't have any breaks. All polynomials are like this, so x squared, x cubed, x to any power mixed with other terms of x to various powers and constants, the polynomials that we know and love. They're always continuous, as are a couple other functions, sine and cosine, things like that. All right, down to the bottom. We had briefly talked about even and odd symmetry when I opened the class yesterday. Here's some pictures of nice even symmetry. Notice that symmetry about the y-axis, symmetry about the y-axis. That mirror of the y-axis, you'll see the exact same thing on both sides. So you just want to remember the symmetry about the y-axis is the title, the technical title for what an even function is. And it's not about that being x squared or something, having some even power or something like that. That's a different thing. It's a even symmetry is symmetry about the y-axis. If either one of these functions were transformed left or right, it would no longer have even symmetry. Odd functions, there's that cubic function that I pointed out yesterday. Remember the symmetry? There's that cubic right there. The symmetry about the origin I was telling you about. That means any point that you take on one side of the origin, the distance and trajectory back to the origin, if you mimic it the other way, will land on its mirror point. So it really is like the center 0, 0 is a little reflecting point. Everything reflects over top of it and lands on its mate on the other side. And the cool thing about it, this sine curve, if it kept going, you think, oh, that's not going to reflect, right? Right. But if you actually take a point pretty far out there and you reflect it over the origin, it'll land on its mate. As long as you keep the trajectory and distance the same on the other side of the origin, you get a mirror point. That's odd symmetry. These odd symmetrical functions, if you transform them left or right in some fashion, there's a way to make them not odd anymore. So if you move them off the origin, they don't have odd symmetry anymore. So let's put that definition, by the way. That is symmetry. I think there's one, I cannot remember. Look at this, it's 5:50 in the morning. You can't. Symmetry with so many M's. There are two in there, right? About the origin. And you can laugh at all the typos and weird things I might say. Okay, symmetry about the origin. Bingo. Now I'm going to do this kind of in real time, so I'm going to add pages, and you guys can see me adding the stuff from my iPad as I go. Sometimes I like to smooth all this out and make it look good, but at this point, we're just working. Okay, so here comes the next one, even and odd. You're to determine even and odd. What this means is, if this were even, how would I finish this drawing? And what I would do is that you just take and you do a mirror image on the exact opposite side. So, oops, I should do a different color rather than red. Let's do green. But if you take a look at this green that I'm attempting to draw, I'm doing this very sketchily. This very sketchy sketch. This is my really, really poor attempt at drawing the reflection. So this is I think, a better image of those functions. These are odd, even, or neither is the question. Now you could graph it if you wanted to, but that can work. In this particular case, I think it would for A. If you graphed it, this is just a parabola shifted down 3. Because it's sliding up and down the y-axis in that case, it would maintain its even symmetry. It would still be just like x squared is even. Moving it down 3, it still reflects over the y-axis. That might be a reasonable call to make, but we'll also use it as an example for when it's not easy to decide. Like in the next one over here, graphically, you can't really figure out. There's an algebraic means for testing whether or not it's even or odd symmetry. So now hang in there, just kind of go with this test, and then I'll try and explain the means behind it. Hopefully that doesn't throw you off too bad, but the test is really quick. I know this one here in A is going to have even symmetry, so what I want to do, here's how it works. We do a substitution of negative x into this function, and what we get out tells us whether or not it's an even function. We already know it is, if you can picture the graph in your mind. So what I mean by subbing in negative x is you take negative x and replace positive x there, in parentheses. Remember substitution, got to keep those parentheses, because if I square that negative x on the right-hand side, it will become good old-fashioned positive x. So here, this can be x squared minus 3. Okay, right after I finish B on this next one, I'm going to stop this video, double check that. I think the video might have stopped recording in a key part, but I'll figure out what it is, and then I'll start the next video and pick up where those pieces are. So just hang in there. There'll be a part 2 to this. Then there's x, so you're okay with the negative x, just went in, squared it, now it's just positive x squared minus 3. Do you notice something? Do you notice that's like the same as what it was before? So here, let me look at that. This is the exact same as what I had before. When that happens, if you substitute negative x in, and what ends up happening is you get the exact same function back again, that's actually an indicator that this has even symmetry. So with that, so this is if f of negative x ends up being the same as regular old f of x after you do your little simplification stuff, that determines this has even symmetry. Okay. Now that sounds, I think the notation of it really is goofy. It looks funny, doesn't it? F of negative x equals f of x. What? Well, it's actually a statement. It means when I put it in, that negative x in, what I got out was the same regular old f of x function. So I wanted to use that example to give you an idea what that definition is saying. Okay. B, we'll do here, we would say, oh, I could graph it and think about it, but I got this cool trick, this algebraic method that is actually much more finely tuned, can handle some more difficult problems. If I put negative x into G, I want to see what I get out. Negative x is kind of like that. I might get the same thing, right? Hey, look, the negative x, it'll turn into positive x squared when I square it, great. But here comes the difference. There's the difference right there. That negative x that I just put in for the other x on the right-hand side, that one, that's going to change the function up. You notice that? Can you kind of see what I'm looking toward here? Look under there. That's going to be different than the original after I simplify. And this one's not going to have even symmetry because I'm not going to get out the same g of x function that I started with. So now that could mean something else. So I'm just rewriting as I go along. So what I end up with is x squared plus 2x, right? Because it's negative x times negative 2 minus 2. We had one little adjustment. That changed sign. That's it. Well, when you put in negative x and what you get out is something different than the original, it has two options. It's either odd symmetry or neither symmetry. This one is neither. Odd symmetry is if all of the terms in this, what I'm showing you right now, if all of them change sign, if it went from negative 2x in the original, let me go up there, and when I was done I had positive 2x, that is a change of sign. If all three terms had changed sign, so instead it was negative x squared and a positive 2 at the end, that would be an indication of odd symmetry. If you put negative x in and you get out the opposite, all the things change sign, you call that odd symmetry. If it didn't stay the same or change all the signs, then we have neither. So I'm going to put a definition on the next page. We have one for f for even symmetry going right now. If you put in negative x and you get out the exact same function you started with, you got even symmetry. If you put in negative x for f of x and you get out the exact opposite, it's odd symmetry. I'll write that on the next page. And if you get neither of those two, well, then you have neither type of symmetry. Okay, so the example C is one I'll look for too when I pause this, but that's part one. Let me add one page, write those definitions, and then I'm going to have a new video loaded up and ready for you guys to go. So here we go. F of negative x means I'm putting negative x into the function, and what I get out is the same thing. Well, that's even symmetry. If you put negative x in there, and what we get out is everything changes sign, well, that's odd symmetry. Okay, looks like that. This, if I hadn't shown you kind of what that plays out, is those definitions these are just the darndest looking things. You don't know what it's saying, but it really just means do a little play around, put this negative x in there. The mathematics behind it, if you are curious, think of this, if I have x squared, a very even function, what we're doing is, if I put in a negative x of any kind, I have a particular output, right? A particular height. Well, it's going to happen to be the same as if I put x on the other side in, I'll get the same output. That's kind of what it's saying. When negative x goes in, it has the same value as when I put positive x in it. That's one way to think of how even functions work. Maybe that helps some of you. Maybe it doesn't for others. Okay, I'm going to show you one more. What about if I do it with an odd function, like our cubic function? Okay, if I put negative x in there, I have a particular output, right? Well, positive x on the other side, when I put in, I get the exact opposite. So if it was, down 3 on the left, it's going to be up 3 on the right. That's that is what the function, what it's saying. This negative x goes in and you get the opposite of what you got on the other side. That's a definition of odd symmetry. For us, it ends up boiling down to a pretty simple little process. If you just, I'm going to back up a page here, or two. For us, it just ends up being when I substitute in negative x, do a little simplifying, look at the result. If it's the same as what you started the original function, it's an even symmetry. If it has all the opposite signs, everything changed from positive to negative or negative to positive, it's odd symmetry. If it didn't do either of those, neither. Okay, part 2 coming.